Chapter, and we have a series of talks. As all of you know, in the invitation also we have sent it, and we have Engineer Narendra Singh, Dr. G. Rameshwar Rao, who is the chairman of Telangana State Center with us. And of course, as all of you know, these are the series of talks that we would be having over the next 3 days. That is the first on sustainable development, second on geopolymer concrete, and third on earthquake safety of tall buildings, some salient provisions of IS 16700. So this series of webinars have been organized, in fact, to give a overview of what's happening in the construction industry, and at the same time to give the developments that is happening in the construction industry. As all of you know, both the Institution of Engineers, which is a professional body of civil, all engineers from various disciplines, and Ramco Cements, which manufactures a variety of cement, 12 brands of cement, have come together to organize this webinar series. What we have felt is that with the type and variety of concrete that is being used, we thought that various types of cement are needed for making economical and concrete mix, which is much more sustainable. And we also have the trimix range of products with us, so which we have been doing. And apart from this, we have the Ramco Research and Development Center, which we have got. So we have various kind of initiatives that we have been having in the recent past, as all of you know. So without wasting much time, let me invite Dr. G. Rameshwar Rao for giving the welcome address. Over to you, sir.
Good morning to all. Respected Chief Guest, Engineer Narendra Singh Ji, President, Institution of Engineers India. Today's moderator, Engineer Anil Kumar Pillai, General Manager, Technical Services, the Ramco Cements, Chennai. Today's speaker of this event, Dr. V L Subramaniam, a professor, Department of Civil Engineering, IITH Hyderabad, and experts from the construction industry, fellow fraternity, a distinguished guest, media friends, ladies and gentlemen. Today I'm very happy and consider it a great honor to amidst this important event, and extend a hearty welcome to the chief guest, Engineer Narendra Singh Ji, President, Institution of Engineers India, and today's speaker, Dr. LVN Subramaniam, KVN Subramaniam, and Engineer Anil Kumar Pillai, and all of you to this important web seminar. It needs no emphasis that engineers play a very important role in every walk of life in development of society and nation. The biggest challenge today before engineers is to see how best the development can take place with the least impact on the environment, and creating the environmental friendly and ecological appropriate as well as energy and water saving and innovation sustainable development, not only for the present generation but also to the emerging generation down the line. To build a nation, it is necessary to make it habitable, the citizenry, for providing the social amenities, that is infrastructure facilities, job creation, security, and many more for the engineers. Therefore, there is a vital role to play. Thus, they are duty bound to design the project, products, and machinery, and plants, and also to design the manufacture of these projects and plants to ensure safety and quality, efficiency, and sustainability against hazards. A sustainable development must, the model is not only for the imperative today, but also opening the new opportunities for the industry sector. And Indian industry should focus on reducing the carbon footprint and devise the green technologies. The sustainable development goal will require action on a number of fronts, including the harnessing and maximizing the potential of technology innovations. And examples such as the technology includes the carbon capture of the storage system and more efficient irrigation method, and essential for medicines, and also household water purification devices and the manufacturing process that minimize the waste and the pollution, while some needed the innovation can be fostered through the existing public and private mechanism at the national level. Such efforts have proven inadequate to meet the global sustainable goals, and particularly with regards to meet the needs of the world's poorest, most vulnerable in the current uh, and future generation. So often the technologies are either are not developed at all for the lack of the sufficient profitable market, nor if developed are not accessible to and are uh, well adapted to the end user's needs. The sustainable development can be defined as the approach to the economic development of a country without the compromise the quality of the environment for the future generation. In the shape of the economic development, the price of environmental damage is paid in the form of the land degradation, soil erosion, air and water pollution, deforestation, etc. This damage may surpass the advantages of having the more quality output of the goods and services. In this happy occasion, it is my privilege to say a few words about our Institution of Engineers to all the participants. The Institution of Engineers is the largest multi-professional body, multidisciplinary professional body, and encompasses 15 engineering disciplines and gives the engineers a global platform from which we can share the professional interest, and established in 1920 with headquarters at Calcutta, and memberships of more than 1 million. And there is therefore we are organizing prestigious centenary celebration this year. I wish to bring kind notice of all of you. The Telangana State Center has been formed after bifurcation of elsewhere Andhra Pradesh State Center since August 28, 2016. The Telangana State Center of the Institution of Engineers has on its roll more than 9,000 corporate members covering 15 disciplines, and engineering besides non-corporate members is 19,000. Um, the Telangana State Center has been most active center of the Institution of Engineers, which is engaged in successful translating the objectives and ideas of Institution of Engineers into practice. The present Telangana State Center is a legacy of the elsewhere Hyderabad State Center of Nizam's Hyderabad State. You are kind of aware that Telangana State Center will actively conducting all innovative programs for the benefit of the budding engineers and the professionals. I am very happy to inform that the Institution of Engineers has entered its centenary year, September 2019, and we are celebrating this significant milestone with varied events in a befitting manner for its glorious contribution to the national development. As a part of centenary celebration, the Institution of Engineers, Telangana State Center of Institution of Engineers, and also all other centers are organizing a series of international conferences, national conventions, all India seminars, workshops, roundtable conferences, etc. in almost all engineering disciplines with the aim to disseminate the latest knowledge and technology to our engineering community. It is relentless journey of 100 years. The institution has crossed many milestones and established significant existence and accredited to the vital contribution towards the engineering and education technology advancement and the industrial and economical development of our country through its 124 state and local centers spread over the length and breadth of the country, and 6 overseas chapters also. The activities are most covered by the in-house programs in various engineering fields, and added that a paradigm shift has taken place in our technologies in advancement in the recent time, which has brought in a few dimensions approach to our fish of excellency and thinking. The institution has the endeavoring to act as a think tank to the government on all the engineering and technology complexities by offering the appropriate solutions and generating the awareness among the general public. The Telangana State Center has organized many events during the centenary year. First of all, the international conference we have conducted, mining present and future investment and issues challenges, 23rd, 25th October 2019. And also international conference on environmental degradation, the key challenges to sustainable development from 22nd to 25th November 2019. And also we conducted during centenary year, the 34th Indian Engineering Congress from 27 to 29th December 2019. In addition to the above, Telangana State Center is also organized one-day seminars, all India seminars, various engineering disciplines. That is, for example, one day of seminar, utilization of Koyna hydro water and diversion of Western Ghat rainwater into Krishna Basin, all India seminar on cyber security and emerging processing, and recent automation and digital manufacturing, and recent developments in technologies, options in the recovery, resource recoveries, and also digital technology in surveying, mapping, and policies of government, the challenges, opportunities in electricity power in India, and also load management in electrical power system. I'm happy to inform that the Telangana State Center is forefront to initiate the webinars in our country, and Institution of Engineers conduct a number of programs through webinar. So far we've organized 24 web conference and panel discussions never since coronavirus it started from March 2020 on various subjects in engineering. In line with the above, the Telangana State Center of Institution of Engineers India has now decided to organize the 3 days national webinar series in association with the Ramco Cement Limited. We are very happy. And also, with these few words, I conclude once again, extend hearty welcome to all of you on behalf of the Institution of Engineers Telangana State Center, and to the chief guest and to all of you. This is the customary to tell about our chief guest, Sri Narendra Singh Ji, has a degree in civil engineering from MNIT, Ahmedabad, and post-graduation in irrigation hydro from University of Roorkee. Narendra Singh Ji served government of Uttar Pradesh and Uttarakhand Irrigation Department with the distinction and the vast experience in project implementation ranging from small and medium scale hydro projects and major hydro structure such as a cross regulatory and composite falls of Madhya Ganga canal projects. Narendra Singh has instrumental in successful rehabilitation of rural and urban families affected by the construction of Tehri Dam project. His considerable efforts during his tenure, he has done wonderful work, and also rehabilitation, resettlement of Tehri Dam and other major projects, power projects in India. Narendra Singh has rendered exceptional services in the Institution of Engineers various capacity. He is the founder chairman of Uttarakhand State Center, and he is credited with the construction of the modern building for the center in cooperation with the government of Uttarakhand. And engineer Narendra Singh has contributed significantly and added value while serving on many important committees and the Council of the Institution of Engineers. He has been a major contributor in various initiatives undertaken in enhancing the role of relevancy and image of the institution. And Narendra Singh has also credited with the focused efforts on promoting the regional language, the first time publishing a book in Hindi also, and also is published a life sketch of Bharatratna Moksha Gundam Vishwesvaraya story in Hindi. Engineer Narendra Singh has been recognized through various awards for his contribution to the engineering profession as well as his involvement in social cause and community development. He has traveled widely on the many countries also. He is actively involved in various professional bodies and has been an executive member of All India Engineers Federation and a member of the National Institution of Hydrology as a life member. He is also active and education sector, and he's created the green environment. He's also been unanimously elected as the president of the Institution of Engineers for the session 2019 and 20. Now it is extended to the 21 by the Council of the Institution of Engineers, which is really testimony of the recognition of his services and the long-standing contribution to the Institution of Engineers. With this few words, I once again extend our engineer Narendra Singh, President of Indian Institution of Engineers.
Thank you very much, Dr. Rameshwar Rao. Thank you very, very. I am really thankful to you. Always you call me on the webinars, although I am not competent persons for all these. Good morning, ladies and gentlemen. It gives me immense pleasure on behalf of Institution of Engineers to welcome all delegates, dignitaries, listeners, stakeholders. You are getting me? My voice is clear? Hello?
It is clear. It is clear. We are able to hear you.
Okay, thank you, sir.
We are able to hear you.
On the webinar on innovations or sustainable development, which is very relevant in the present scenario. I congratulate the organizers of Telangana State Center and Ramco India Limited, Ramco Cement India Limited on the occasion, and wish the success of this webinar. As you are well aware that Institution of Engineers is the largest multidisciplinary organization of the engineer, and it was established in 1920 and was incorporated by Royal Charter in 1935 by King George V of England. We have come in 100th year of its establishment, and already we have started celebration functions which was beginning on 13 September 2019 at Chennai, where this institution was first registered. We have celebrated 23rd February 2020 at Asiatic Society of West Bengal, where the first Indian President, Sir R.N. Mukherjee, addressed the AGM, first AGM, in the presence of Viceroy General of India. Friends, institution is doing a lot of technical activities to for the advancement of our country. We are involved in many ways, achieving the goal to progress, to enhance our country, to give support in the technical matter, in the development of our country. We have achieved many milestones and many are still to be achieved by this institution. We are really proud to have legacy eminent engineers who led our organization, such as Bharat Ratna Vishweswaraya ji, R.N. Mukherjee, Dr. A.N. Khoshla, Dr. Tribhuvan Sen, Padam Bhushan, Dr. K.L. Rao, Satish Dhawan, U. Ramchandra Rao, and many more who excellent contribution on the foundation and development of our country. In 1935, George V accorded prestigious Royal Charter by virtue of his engineer attached to this institution are known as Chartered Engineer. Prior the formation All India Council of Technical Education, AICT, Institution of Engineers used to serve as a prestigious job for regulating engineering and technical education in the entire country. The development of a nation are normally classified into three categories, which are technical development, industrial development, and economical development. Engineers play a vital role in the development of a country. Human resources is our best strength and can be real resource for us. It can be utilized through the proper training in the engineering. Practically, all the professions such as agriculture, engineering, medicine, media, industry, finance, management, etc. are dependent on the modern technologies. There are a number of success stories of technology development in our country. Irrigation, power, space, missile technology, and telecommunication, nuclear technology are some of these examples. I sincerely believe that to fulfill our dream of a developed India, engineering and technology is the key factor. I hope that Institution of Engineers India, which is the largest body of the professional engineers and technologists, have a crucial role to play towards furtherance of engineering profession and overall development of our country. Friends, I am proud and feel proud that if you want to change the world, you for better, please become engineer. It is my saying, not mine, but everybody says an engineer can give everything, which is nothing is impossible in his directory. Engineers and engineering are critical for achieving innovation in sustainable development. Engineers are essential for a peaceful world, as engineers who will develop the implement innovation in sustainable development as they relate to water, energy, environment, sustainable sites. Yes, it has gone. Engineers are essential for reliance and climate change and to develop resilience in infrastructure that will withstand the increasing weather-related events, flood, cyclone, bushfire, especially in the developing countries that are most exposed to these risks. Engineers are essential for sustainable economical development as they are needed to support the growth and development of essential infrastructure such as roads, railways, bridges, dams, waste management, water supply and sanitation, energy and digital network in both developed and developing countries. Engineers are needed to develop inclusive technologies and innovation that will benefit the people and the planet for greater prosperity and better quality of life and leave no behind, especially to ensure equal access to technology for women and in rural areas. Sustainable development is the opportunity to discuss these issues and engage wider community in the contribution of engineers and engineering to work, and it is the need of today. It is our day when engineering and we are discussing innovations in sustainable development goal. I again repeat my word, if you want to make change in the world for a betterment, become an engineer. Thank you very much. I am a field engineer. I don't have better speaking power, but I can express something which related to the fields only. Thank you, sir. Thank you very much.
Thank you, Engineer Narendra Singh ji, for that address, and it was really very inspiring because being a professional who has worked in various departments, and I'm sure that you would have come across various challenges. And most of the participants who have joined us, if you have any queries on Institution of Engineers or something like that, how to join it, questions relating to that can be put towards the end. You can put it in the chat box, and I'm sure that our panelists would be ready to address them. So let me just come to today's talk. Today's talk by Dr. Subramaniam. In fact, as all of you know, that he has this is the second talk that he is making. Earlier, he had made a talk on admixtures. So let me just give a brief introduction of Dr. V L Subramaniam, who is professor at Indian Institute of Technology, Hyderabad. He was awarded PhD in Civil Engineering from Northwestern University, USA, and MS in Civil Engineering at University of Toledo, USA, as well as he had done BTech in Civil Engineering from IIT Delhi. And at IIT Hyderabad, he worked as Dean, Planning and Development, Head of Department of Civil Engineering, and at present, he is Professor. Previously, he worked in City University at New York Civil Engineering Department as Professor and Director Civil Engineering. He also is a cattle research fellow, associate professor with tenure, assistant professor. He has worked at NSF Center for Advanced Cement-Based Materials, Northwestern University, Evanston, IL as research associate. His areas of interest are behavior of concrete and masonry structure, alkali-activated binders and geopolymers, rheology control and 3D printing, fiber-reinforced concrete sensor development for concrete structures and infrastructure monitoring, low-cost housing solutions with prefabricated elements, repair systems, and strengthening of concrete. So may I invite the speaker of the day, Dr. Subramaniam, to give away, to start off with his presentation on this very interesting topic on sustainability. I think yours is you can unmute your mic, sir.
Yeah, okay. So thank you, Dr. Pillai, thank you, Institution of Engineers, India, Rameshwara Garu, Narayan Singh ji, for giving me this opportunity to present on a topic which is basically, it's a cliched topic, sustainability. It's been used a lot, misused a lot, abused a lot. So I think it's time we addressed this topic in a careful, scientific manner. And as the president mentioned, maybe look for engineering solutions to this. So, and civil engineers in particular, I think have a very key role to play in this sustainability. So I'll focus particularly on concrete in particular, and what has been done, can be done, and should be done to ensure that to ensure its sustainability. That being said, I think I'm coming across to you on this medium, which is basically where we are all scattered. If it's a pan-India webinar, then we are basically connecting thousands of kilometers, and all of us are hopefully working in a safe environment, probably from the safety of our homes. But this is a challenge. It's probably going to, it has led to a lot of stuff. From here come opportunities. I think we also need to look at opportunities from this challenge that has been thrown at us. And as engineers, I think we have prevailed. We've come across this or come up with solutions which includes webinars of connecting people who are sitting thousands of kilometers away. So that being said, I'd like to start my presentation. I'll silence my video so that I can save on the bandwidth. Would ask everybody to please mute their mics so that we don't pick up any echoes. So starting off, like I mentioned, I'd like to talk about innovations in concrete for sustainable construction. So if I start off, what is this material? It's actually the second most widely used material on this planet. It is second only to water. What is the material we consume? It's about 2 tons per year for every human on this planet. So in terms of its usage, it is enormous. So obviously that comes with a very large footprint. And for us to be sustainable, then we have to look at the issues that come about from the usage of this material. Now, concrete is made with cement. If you look at cement, the past, present, and the future, now this is the cement production as it was 2 decades back, what it is today, and what it is expected to be in the future. So if you look at the red, that is the Chinese dragon, they are the largest producer today, and that's because of all the enormous development in infrastructure in which they invested, which has allowed them to become the second largest economy in the world. Now the blue there is India, and we are on the cusp of basically enhancing our investments in infrastructure. We need that investment, and the current estimate is about $2 trillion of investment has to go into infrastructure if we are thinking of becoming a $5 trillion economy. And that is needed in critical sectors like infrastructure, and infrastructure primarily in highways, roadways, transportation, structures, and water systems. So this is all needed to be able to support the growth that we are projecting. The 7-8% growth that we want in our economy will only happen if we have the infrastructure to support it. And that infrastructure can only be developed if we keep producing concrete. And that concrete can only be produced if we keep producing cement. And the projection for India is by 2050, we'll probably be the largest producer of cement. Of course, this is a projection. And to sustain it, then we need to find what are the challenges in continuing this production as assuming the business as usual model, or do we need a disruptive change where something has to change, and what are the challenges there? Now, what the biggest challenges in cement production? Well, one of the biggest challenges in cement production is raw material. I mean, if you look at our projected demand of cement in 2050, we need 750 million tons per annum to meet our demand, and that is an enormous demand of cement. The challenges that we have is that the current availability of limestone is a critical ingredient that goes into making cement. Basically, our best estimates are that the limestone is going to last us another 35-40 years, which means the business as usual model will not work. We have to look for alternate solutions, alternate materials, alternate cements. So that has to happen because the material, there is a material limitation. Cement is not is a material that has a very high energy requirement. So producing cement requires high levels of energy, and we have to gear up to be able to produce the energy. And as a material, it has a very large carbon footprint. In fact, it is the second or third largest anthropogenic source of carbon in the atmosphere, or carbon dioxide in the atmosphere. So it has a very large carbon footprint. So in terms of environmental impact, it has a very large environmental impact. So these are the current challenges we are looking at, and cement industry has to gear up looking at these challenges, because without cement there is no concrete, and without which we will not be able to produce the infrastructure that we need. So what about construction? Now, coming to construction, when we are looking at construction, we are still stuck in the old form of construction, particularly dealing with concrete. We still assemble formwork on site, and then we pour concrete, we let it harden. It's a 28-day process. So A, it is time consuming. B, I am limited to what I can produce in the field. And oftentimes that is not the most efficient use of material. So when I'm talking about rectilinear shapes, primarily rectangular shapes, most of our beams and columns are rectangular, and that is driven by constructability, because this is what we can construct with ease. So, but these are not the most efficient structural shapes, which means we're using material more than we are required to, and of course that increases the material demand. So we need better forms of construction which allow us to go and produce shapes optimally designed structurally. And suppose I wanted to produce a shape as I've shown here on the left hand side, producing that on the field is not possible, which means we need to come up with new construction technology, which basically takes us into a new domain of form-free construction, where we are talking about construction without the use of formwork. And that's a new challenge that has come about from the construction side of concrete. Then we're talking about challenges in construction. We're talking building faster now, because now gone are the days where we would like to wait for years, and quick turnaround has become important. And some of the stumbling blocks that we encounter when we're building faster with concrete is on site. While advantage forming on site, it's also a disadvantage, because I have formwork cycle times. Basically, formwork takes time to assemble, then it takes time to disassemble. I need skilled labor. And of course, reinforcement has to be integrated with it. So it's a time-consuming process. And oftentimes, this is what slows down concrete construction. So we really need to look at this in order to have efficient construction, which not only addresses the material demand, that is, we use the material in a very efficient manner, but also have efficient construction technology, which allows us to build faster, basically essentially getting into the domain of looking at construction maybe from a manufacturing perspective. So looking at construction technology and bringing in newer forms of construction technology, which allow us to basically overcome these traditional roadblocks which have come about from the traditional way of thinking. So we have to start looking at things more from a manufacturing perspective. And we are heading in that direction, where now we're talking about additive manufacturing and 3D printing of concrete, which basically a lot of research is going on. And slowly it will become mainstream in construction. So what are the solutions? I've listed the problems. Now, clearly cement is the backbone. We have to look at cements. So we have to look at alternate cements. So we have low clinker factors, and clinker is what goes into making cement. It is the essential material that goes into making of cement. Clinker is ground to produce cement. So we have to minimize our clinker usage in cements. That will basically lead to a reduction in the cement utilization and will allow us to stretch our resources for more time. The other alternative is to look at alternative clinker-free cements. So basically look at cements which are basically not produced using limestone or using the Portland cement manufacturing procedure, but maybe making cements from waste material, which basically is the ultimate paradigm in sustainability, because then we are very sustainable. We are essentially utilizing waste material from other industry to produce something that is useful in our particular usage. Then alternate reinforcement, and this is one of those things that is now being thought about, because if tying of reinforcement, laying of reinforcement is a problem, then maybe we can think of integrating reinforcement with concrete at the time of mixing, and then providing reinforcement as and when it's needed. So which also basically allows us to bring in alternate forms of construction technology. Efficient construction. So we are talking about identifying the labor intensive processes which slow us down, and looking at form-free construction, basically printing concrete, delivering concrete in the shape we want, shapes which have been optimized for structural efficiency, so that we use the optimal amount of material and not what is dictated by what formwork I can assemble on the site. The final thing, which I did not allude to before, but is becoming very, very important now, is managing the energy demand. Now, as India is becoming richer, as most countries in the world, as they're becoming more affluent, the energy demands are going up. And the biggest requirement of energy in today's world is going into cooling applications. We, as urban centers are growing, people are demanding alternative methods of cooling, including air conditioning, to keep the buildings cool. And basically, we have to address the requirement of energy for this energy, for providing the cooling needs of the urban society. And that basically is something that can be addressed in a passive manner by thermal efficiency. So if we can have buildings which are designed such that they're thermally efficient, so that the heat gain of the buildings is low, then the demand for cooling would also decrease. And this means that we look at construction material which are thermally efficient, so that we can reduce the heating requirement for cooling of these buildings. So these are basically the different aspects that we need to look at in order to basically look at concrete construction technology, and look at sustainability from material, energy, and a carbon footprint point of view. So a little bit of background about cement. Cement is basically a material that is primarily a calcium silicate. The way it's made, limestone is the primary ingredient. We use clay and limestone and heat it together. And these are heated to a temperature of about 1600 degrees Celsius. So that's where the energy demand for making cement comes. Now, because I use limestone and clay, the primary ingredients that go into cement are calcium silicates. Limestone gives us the calcium, and the silicates come from the clay, and basically it's a calcium silicate material. And basically everything that has come about from cement, when we mix it with water, and as it hardens, as it gains strength, it's basically driven by calcium silicate chemistry. And that is what we have been using for past 2 centuries in the form of Portland cement. Little bit of chemistry, basically calcium silicate. So what you see here, these are tricalcium, dicalcium silicates. Those are the main ingredients of cement. When they react with water, which is shown with the H here, it produces CSH, the calcium silicate hydrate. This is that material that gives strength to concrete, the calcium silicate hydrate. It also gives off a lot of CH, which is calcium hydroxide, which makes concrete very alkaline. So basically, concretes are very, very alkaline. They produce a lot of calcium hydroxide. And the calcium hydroxide is basically doesn't contribute to strength. It's just a byproduct of the reaction. So one of the earliest attempts to basically reduce the clinker is what basically gives us these calcium silicates, was to look at this calcium hydroxide, which is sitting idle in the system, and utilize it by dosing additional forms of silica. And as luck would have it, we found additional forms of silica from waste materials. And these are identified with slag, fly ash, metakaolin. These are all materials, especially slag and fly ash. These are waste materials coming from other industry. Slag is a waste material which comes about during the refinement or during the process of extracting iron from iron ore. And fly ash is what we get when we burn coal to produce electricity. And it's the ash that is left behind. That is what we call fly ash. And both of these materials have silica in them. So when I can have an extra source of silica, which I add to the cement, that silica is able to utilize the calcium hydroxide that is given off by the cement reaction, and basically is able to produce additional CSH. Basically, I produce additional calcium silicate hydrate, And we discovered these have been in use. So that has allowed us to reduce the clinker factor of cements. And now the cement companies working with the researchers, working with the standardization agencies have basically standardized the use of addition of these supplementary cementitious materials. So slag, fly ash, metakaolin, these are all supplementary cementitious materials, which are used as a replacement of cement in Portland cement. So now this has become commercial, where we're able to reduce the clinker factor with the use of these waste materials. So just to give you a little background of these waste materials, we use slag in a granulated form. It's basically the junk or the gunk that floats on top of molten steel that is quenched very quickly, and it basically produces a highly reactive glass, which is what we know as slag. And the slag is very rich in silica and calcium, which are basically the main ingredients of cement. And so we are able to use it as a cement replacement. Metakaolin is actually something that we produce by calcining clay. We calcine clay at 650 to 700 degrees Celsius. It's moderately reactive, but again contains silica and calcium. Therefore, we are able to use it as a clinker replacement. But coming to fly ash. Now, fly ash is basically a waste material that is produced by burning coal, and basically it's a grayish powder which is produced because of burning of coal. And fly ash, it's a low reactive material, but it contains silica and calcium. So if we look at silica replacement in cement, the way it works is that if I look at cement, I have calcium, silica, and alumina. And if you look at any of these waste materials like slag or fly ash and metakaolin, they basically contain calcium oxide, silica, and alumina. And I'm basically looking to replace the silica in the cement with the silica that comes from these waste materials. So basically, as a silica replacement now, this has become very standard. Replacement of cement with these waste materials is now a very standard way of reducing clinker factor in cements. So coming to fly ash now, fly ash basically, if you look at this world map here, the countries in red are the ones which are the largest producers of fly ash. India, of course, is the second largest producer of fly ash in the world today, second only after China. Now, for us, fly ash is a big concern. The reason is India relies very heavily on coal burning power plants to produce electricity. So somewhere around 75 to 80% of our power needs are met by coal burning power plants. The issues that we have is that the coal that is consumed in India is an inferior grade coal. So it basically produces a lot of ash. The ash content of coals tends to be as high as 50%, which means 50% of the coal that I burn is left behind in the form of ash. The average number is around 32%. Now, the problem we have is the gap between the production and the consumption. So if you look at the gap here, the graph here, the blue lines indicate the production of fly ash and including the expected production of fly ash. The green bars show the consumption of fly ash. So we are even today lagging behind in the consumption. Even today, our consumption of fly ash is around 60–65%. The remaining part of the fly ash is remaining unutilized. Now, of course, fly ash is a very unreactive material. One cannot grow plants on it. It is not directly usable in other industry. Therefore, this presents an opportunity for us. On the one hand, we have a material that is being produced in plenty. Disposal of that material is an issue. On the other hand, it has certain properties which allow us to utilize it for making cements. It is already being utilized as a cement replacement, but perhaps we can push it further and look for alternate cements. And that is the issue. But one of the challenges we have with fly ash as it is produced in India is the large variability. We have a very large variability in composition. I'll show this in the next few slides. Is that there's a large variation between source to source. So if I collect fly ash from 3 different power plants, I'll get very different reactivities. I'll get very different compositions. The variability in the raw feed, even if I look at the same source, because the coal that is burnt is different, it keeps changing. Even from the same source, the fly ash is not of a consistent quality or of a consistent composition. So that makes using this fly ash a little bit of a challenge. It is low reactive material compared to fly ash produced in other countries. fly ash produced in India is not as reactive. So we started studying fly ash just to understand it, to see how we could maximize the utilization of fly ash. And if you actually go to look at fly ash under the microscope, you see that it contains, it's a very complex material. It contains these iron-rich particles. It has a lot of quartz in it. And if you look at quartz, quartz is basically silica and oxygen. Basically, it's silicon oxide. And a lot of the silica that is present in the fly ash is present in the form of quartz. And the problem with quartz is it is one of the most unreactive materials known to man. It is sand, basically. And sand is, as we know, is not reactive. There's a lot of unburned carbon in Indian fly ashes, and unburned carbon means two things. One, we are not utilizing the carbon properly, which means the boilers are not, which are used in producing power, are not effectively utilizing all the carbon present in the coal. That's why a lot of it is showing up in the ash. The second problem is that if carbon is present, it basically starts absorbing water, it starts absorbing admixtures that we add into concrete, and basically makes those admixtures effectively useless. And that's one of the big challenges in using this fly ash. But fly ash contains these spheres that are present in them. These are basically spheres made of glass. These are alumino-silicate glass. And it is those spheres that we're interested in. These spheres are called cenospheres. And if you look at the cenospheres, more shots of the cenospheres, it is this glass content in the fly ash that we're interested in. It is that glass content in the fly ash that contains the reactive silica that we can then use as when we are trying to substitute clinker, when we're trying to cement with this fly ash. So we started looking at fly ashes across India. We collected fly ashes from different power plants, thermal power plants, and they're labeled on the top, BDK. Those are the different power plants. And when we did the oxide analysis, we found that the oxide analysis indicates that more or less the main oxides, the silica and the alumina present in the fly ash, are consistent. But when we started using them in cement, we found that the results were very different. So clearly, only the oxides, as indicated by oxide analysis, are not indicative of the reactivity of fly ash. The other thing is there is very low lime content in our fly ashes. It basically contains very little calcium oxide. So this is a unique characteristic of most Indian fly ashes, where they're very low in lime content. The silica and the alumina contents by themselves are not indicative of the true reactive potential of these fly ashes. And reactive potential is important because when I'm looking at replacing cement, which is a very reactive material, I need to see how much of cement can I replace with fly ash. So therefore, I need to assess what is its true reactive potential. And unfortunately, just looking at oxides, we are not able to infer the reactivity. So we went further. We started looking at the different glasses that are present that can be formulated. And we found that the glass that is present, these are the X-ray diffraction signatures of different glasses that we formulated in our lab. These glasses are synthesized. And we found that the low calcium fly ash, basically, which is given by C and A, this is the X-ray diffraction signature. The X-ray diffraction signature of most of the fly ashes that are present in the glass that is present in most of the Indian fly ashes is a low calcium type glass, the C and the A. And such glasses, as we look at the chemistry, is basically inherently non-reactive. The other thing is, I just wanted to show you the X-ray diffraction signature of a fly ash. The black line here shows the X-ray diffraction signature of a typical fly ash. A good percentage of the fly ash contains quartz, the quartz that is shown here. Now, quartz is basically also silica, which is present in a very non-reactive form, in the form of sand. So a lot of our fly ash comes loaded with silica, and what you saw in the table above, the SiO2 that you see, a lot of it is locked in the form of quartz, which is non-reactive. What we need is the amount of silica that is present in this glassy phase, which is shown in the red line. So we developed a methodology to basically look at what is the reactive part of the silica of the fly ash, which is present in the glassy form. And we found that, unfortunately, our fly ashes have low reactive silica in them. It's only 10 to 25% by mass of the fly ash. So if I take 1 kg of fly ash, only about 250 grams, or sometimes it may be as low as 100 grams of that total fly ash is present in a reactive, is present in reactive silica form, which I can then use as cement replacement. And because it has a very low lime content, it does not have any hydraulic action, which means if I fly ash with water, it is not going to react because there's no calcium present in it. So but then we started looking at what are the differences, and I will show that to you with this bar chart here. These are the fly ashes collected from the different thermal power plants. And what you see here, the blue lines indicate the total silica. I have already shown that to you in the tabular form. The green lines are the silica that are present in the reactive form. And you can see the differences now. While the differences in the blue lines are not significant, basically the variation is not very large, you can see the green lines, they're much smaller. So when I have something in the range of 50% of total silica, the reactive silica content varies, and it's actually much smaller than the total silica content. So when I'm looking at clinker replacement, when I'm looking to replace cement with this fly ash, only a small percentage of the fly ash is useful in that regard. And basically, I just show you this. This is one particular fly ash which is used or is being used quite a bit. And you find that it has only 13% reactive silica, but it's being used quite a bit as cement replacement. So we really need to understand our chemistry in order to optimize how much silica, how much fly ash we can replace in cement. And we've developed now algorithms and procedures which allow us to optimize exactly the amount of fly ash that we can basically replace in cement, so that we don't compromise the properties that come out of this blended cement, where we are using cement and fly ash together by looking at the reactive content, reactive silica that is present. The other thing I want to point out is the reactive alumina. Fly ash also contains alumina, and alumina is also a reactive material. Although in traditional cement chemistry, which is basically calcium silicate chemistry, we do not consider alumina, but it is present there. And if I look at total alumina in the fly ash, it is typically anywhere from 27 to 30%. But the reactive form of alumina is always a much smaller amount. Now, in traditional cement chemistry, we do not talk about alumina, but then when we start looking at alternate cements, the alumina starts playing a critical role, and I'll talk about that in the next few slides. So the fly ashes that we have in India, we are producing plenty of fly ash in India. We are not able to use it, and the biggest challenge is that we need to look at each fly ash individually. We need to identify the reactive silica that is present in there, and then figure out what is the optimal replacement level of this fly ash in the cement. Some reactive fly ashes, we may be able to replace as much as 50% of the clinker with fly ash. The non-reactive fly ashes, we may not be able to go beyond 10% replacement. So the code of practice currently caps off the replacement level of 35%. That's an average number that's given. But if we optimize it, we should be able to go higher or lower depending upon the reactive quantity that is present in the fly ash. But of course, that requires that we need to classify our fly ash. That is, all the fly ash that is being produced, we should be able to do an oxide analysis and then determine what is the optimal use. Now, this is already in practice, like I mentioned. So if you look at ordinary Portland cement, clinker is basically what comes out of the kiln. When I burn limestone and clay together, I produce clinker. And it is basically ground with gypsum, and this is what we get as ordinary Portland cement, OPC. But now already in market commercially, clinker is interground or mixed with fly ash, and it's available as PPC. We also add slag with clinker, and that's also available as in the form of the Portland pozzolana cement. And the difference is because slag is much more reactive than fly ash, we're able to replace a larger percentage of clinker with slag. Whereas when we use fly ash, we are able to replace a smaller percentage of clinker. Now, this is already happening. This is already available in, these are available in the market as PPC cements. Now, going forward now, what other forms of cement can we use? Now, the current form of Portland cement as we use it is 200 years old. The technology has not changed much, except for perhaps improving the efficiency of manufacturing, but the primary technology has remained the same, and it is primarily calcium silicate chemistry. Now what we are starting to look at is alternate chemistry, where we're trying to look at producing cement which are not calcium silicate based. The alternate forms that we're looking at are alumino-silicate based. So basically these don't rely on calcium as their base for strength, but they rely on alumina as their base of cement. And if you recall, fly ash had a good percentage of alumina in it. So therefore, now I can start making these binders or these cements using only fly ash, and that is the beauty of these alumino-silicate binders. The alternate forms of binders that we're looking at are magnesium-based binders, and these draw upon the fact that there is a lot of magnesium that is present in the crust of the earth and in ocean water, in the waters of the seas, is to somehow be able to harvest that magnesium and make cements out of there. Now, with these binders, particularly the alumino-silicate binders, we need silica and alumina. We need a source of silica, we need a source of aluminum. And basically, fly ash contains both of these. Therefore, I should be able to make these cements using only fly ash. And we also have other waste materials like slag, rice husk ash, what we get by burning rice husk, metakaolin. These are all materials which are essentially waste materials, which can be used as a source for making cement without the requirement of clinker. So this is alternate chemistry, which is at work here. And the way it works is that we start with fly ash, which contains reactive silica and alumina. We basically activate it with alkaline activators. We mix it with highly alkaline solutions of sodium hydroxide and add some sodium silicate to it. With sodium silicate is water glass, which is basically used in the manufacture of soaps. And then when you subject it to a little bit of temperature, about 60 degrees or 85 degrees curing, we're able to produce a binder which goes by the name of NaSH, sodium alumino-silicate hydrate, which basically is stronger than cement-based binder. And this is basically does not use any energy in the processing, except of course a little bit of temperature that may be required for curing, to produce binders which are stronger than cement. And these alternate binders are already have been researched quite extensively in the last decade or so, and now they're slowly basically finding their way into mainstream use. The other alkali-activated materials we're talking about is to alkali-activate slag. That is, you start with slag, mix it with an alkaline activator, and because slag contains a higher percentage of calcium, we produce a binder which is calcium alumino-silicate hydrate. So again, here there is no cement in use. It's a binder made completely out of slag. So these are alternate forms of binders that we are starting to experiment with. And basically the chemistry is very different than what we've been used to for the past 2 centuries. And therefore it's taking a little bit of time to evolve. Basically, we have to start with the source materials, which is and we end up producing materials which are aluminosilicates, and they also go by alternate names as geopolymers. So basically, geopolymers are now being looked at as alternatives to cement for producing concrete. Now, one of the big issues here is that currently the production of geopolymers happens in very alkaline environment. I need 8 molar sodium hydroxide solution and higher. So what people have been using are very, very alkaline solutions, and these are very difficult processing conditions, because very alkaline solutions of sodium hydroxide are very pungent. So basically it's very difficult to use. They're very corrosive, and a little bit of temperature is required for activation. That's what are the current challenges. Now, we have at IIT Hyderabad worked with understanding the chemistry of it, and by understanding the reactive silica and the reactive alumina that is present in it, we have developed and patented procedures which basically allow us to now optimize the activation solution that is required. Basically, by starting with the fly ash, we characterize it, establish its reactive potential. Then we optimize the dosage of sodium hydroxide. So we are able to basically optimize it and bring down the molarity, the processing conditions, to 3 molar sodium hydroxide, which is a far less corrosive material than 8 and 10 molar sodium hydroxide. It makes it friendlier to use with the use of sodium silicate, and we're able to optimize it, and we are able to produce binders which basically give us 80 megapascal strength. So this is cement made completely out of sodium, made completely using fly ash, which is activated using sodium hydroxide and sodium silicate. And we're able to hit compressive strengths which are basically on the order of about 80 megapascal. And we're also able to bring the processing temperature down to 40 degrees Celsius. So basically now we're able to process this material at 40 degrees Celsius, which is basically a hot summer day in India. We're able to give strength, very strong material which can be used for making concrete. This process is now has been developed by us, where we take the fly ash, we optimize the binders, we're able to package this material in the form of a cement, where simply you take it, mix it with water, and you can use it to make concrete, which is very, very strong. So to overcome the problem of requirement of temperature, where even using only fly ash, we need temperature of about 40 degrees. We've developed room temperature cured material, which basically can be cured at room temperature, which is about 27 degrees, by blending fly ash with slag. So we basically take fly ash and slag, then we optimize the binder, the sodium hydroxide and the sodium silicate that's needed, which gives us the calcium alumino-silicate hydrate. And we're able to achieve the same strength at room temperature. So now we have this product that basically is stronger than cement, made using completely made out of waste materials, which can be looked at as an alternative to Portland cements. So this is a technology that is now coming into mainstream. And what makes it sustainable is we are basically addressing two problems, where we are essentially finding a way to dispose of waste material, which currently is being produced in excess of its consumption. And second, we are basically tackling the issue of the energy and the material dwindling of materials that is facing us when it comes to production of ordinary Portland cement. And thirdly, the energy and the carbon footprint of these materials, which are alkali-activated fly ash and slag, are practically zero, because here we are essentially using waste material from other industries. So it basically is a form of beneficiation rather than a footprint of energy or carbon associated with it. Now, the other forms of cements that are also being actively explored around the world are magnesium-based cements, and the whole the issue here is biomimicry, and the issue is that the shells, our bones in our body, reefs, coral reefs in the sea, these are all essentially magnesium-based materials. Magnesium is available in plenty in oceans. And the process of biomineralization, by which these are bound into hard materials, as a hard cement-like material, takes several decades and millennia to form. Now, the whole point is to mimic this process, except speed it up. So there are processes that are being developed where we mimic this process, except it is speeded up. It is basically produced in a much faster rate to give you magnesium-based cements. Several groups around the world are now working on these magnesium-based cements. Some patents have been taken out, and these are essentially magnesium silicates. And one of the biggest advantages, as it's being touted, is that these magnesium-based cements also sequester carbon dioxide. So basically, they're able to essentially absorb carbon dioxide, where it's presumed that every ton of the cement or hardening cement essentially would absorb about half a ton of carbon dioxide from the atmosphere. So these are all alternate developments of not only reducing cement consumption in concrete, but to look at alternate cements which do not rely on the old calcium-based chemistry. What is one challenge that we face in mainstreaming these alternate cements is long-term durability. Now, the whole point is that if I build something of it, and say 10 years down the road, it just crumbles. It basically starts deteriorating from some mechanism that we haven't seen it yet. So basically, we are starting to now address this issue of durability. A lot of studies are going on to understand how durable are these materials. A lot of these studies are aimed at doing rapid testing. So because I cannot wait for 50 years to look at results, so a lot of accelerated tests are going on to determine the durability of these materials. And it's a matter of time when we have enough comfort in using these materials that these materials would become mainstream. In the meantime, there are alternate uses that are already coming and becoming mainstream with these materials. So the Geocrete, which is basically made by alkali activation of fly ash, is already coming mainstream because of several advantages that it has. And one of the biggest advantages it has is that it's highly acid resistant. The geopolymers that are made by alkali activation of fly ash are extremely acid resistant. So it's being used to basically to make these pipes which carry a sewage or waste. And most of these pipes, of course, are made out of concrete, but concrete is very prone to attack by acids because the medium that these pipes carry is acidic in nature. And basically, we are right now working with pipe manufacturers who make these pipes from precasting. So because of precasting, they use elevated temperature curing. So we basically would be able to use the same curing procedure as it's being used in current precasting procedure, use temperature to our advantage to produce these precast pipes, but now they're made of geopolymers which are extremely acid resistant. We are also looking at tunnel liners, which are basically used to stabilize tunnels, lining of tunnels behind tunnel boring machines, which are currently made of precast concrete, but we're looking at precast geopolymer liners. The other application that we're looking at is energy. Now, this is energy gains into the building. In India, most of our energy or energy concerns in buildings is concerned with energy gain into the building. And most of our energy gains come through the building envelope. The building envelope is the skin, the outside part of the building, which is in contact with the atmosphere. And mostly it is in the form of non-structural walls and windows. So that's where most of our heat gains into the building happen. And conventionally, most of our building envelope is made out of masonry, conventional masonry, whether it is fly ash brick masonry or clay brick masonry. Now, in terms of volume of usage, these non-structural masonry elements constitute a very large volume of the material that is used in a construction site. So it's a very large volume, and they contribute tremendously to heat gains in the building. Now, and these are non-structural. Typically, these elements do not carry any load on them because they're used as infills inside concrete structural frames. Now, we're working on producing the cellular geopolymer. So basically, cellular geopolymer is where we introduce air bubbles into this geopolymer material. Introduction of these air bubbles basically reduces its thermal conductivity tremendously, and thereby we are able to reduce the heat gains into the building because it's a very low conductive material. And the current material that's in use considerably goes by the name of autoclaved aerated concrete blocks. These AAC blocks are conventionally made with cement binder. So we use cement, and in the cement binder, air bubbles are introduced, and then they are cured in an autoclave. Now we are basically using the same process of autoclaving, except the base material we are using is an alkali-activated fly ash, derived completely from fly ash, and we are able to produce the same AAC, except they are now AAG because they are autoclaved aerated geopolymer blocks, which have very low thermal conductivity for use as non-structural masonry. And we've gone one step further in producing these non-structural wall panels, which can basically, we can now make these wall panels which are aerated and autoclaved, which have low temperature, very low thermal conductivity. And using these wall panels now, we are able to also speed up construction. So this is one of the issues. When we have a masonry infill, so this is a photographs that you would have seen before. This is the structural concrete frame, and you see the masonry infill here. So this masonry infill is a labor-intensive process. Usually, it slows down the construction of the building, and it is a non-structural element. If I can now make these in the form of panels, which are ready to assemble on site, these individual panels can be assembled much faster. They are made of a material which is of thermally of a very low conductivity. So I have I have gains in terms of thermal efficiency. At the same time, I'm able to speed up construction, and it's almost 7 times faster, making my construction also more efficient. So this is another innovation that we are pursuing, basically, which allows us to make construction more efficient and faster in order to meet our goal of faster construction. So now that's as far as the material innovation goes, to meet the energy and the material, overcoming the challenges in terms of material shortages and carbon footprint. Now, the other issue is the use of reinforcement. And one of the reasons we use reinforcement in concrete is for ductility. And I'm showing you this photograph to illustrate ductility. Most structural designers, this is what we aim for, is if I can design a beam which deflects but doesn't fail, that is considered a very good design. It's a very ductile design, and that's what we shoot for when we try to design our reinforced concrete structures. So unfortunately, in order to deliver that level of ductility, often when it's in demand in high seismic regions, we need a very high amount of steel. And I'm just showing you a photograph of such a steel column, beam column joint. This is where beams and columns intersect. The requirement of steel is so high oftentimes that it becomes impractical. We don't have place to put concrete in there. So now what we're looking at is discrete reinforcement. So instead of having steel bars, conventional steel reinforcement, can we start looking at the same steel which is provided in the form of fibers? The advantage again is if I have a steel bar that is placed inside concrete, the steel bar is not effective till the crack comes and intersects the steel bar. So that means the crack has to form, and it only encounters resistance once it crosses the steel bar. Whereas if I take the same steel bar, chop it up into smaller fibers, then every time a small crack forms inside the concrete, it is locally arrested. And basically the local arrest mechanism allows me to enhance the ductility of concrete without having to A, use more steel, and B, using steel in a friendlier format. Here the steel, when it's in the form of fibers, can be mixed with concrete and simply cast with concrete. And so the whole point of fibers is that if I have fibers, instead of one big crack being formed in reinforced concrete, I'll have 50 small cracks that are formed. Now, the rule when we're trying to deal with cracks is that 50 small cracks, if they're very small, will not allow water to get into concrete. And therefore, it basically also enhances the durability of the material. Whereas if I have one big crack, water can get in and steel will start corroding. So this is the role that these steel fibers play. They toughen the material, they increase the toughness of the material. Now the material is able to absorb a lot more energy, and basically I'm able to design using this material. And one of the ways we look at toughness is to see how much effort it takes for us to pull the piece of concrete apart. Because concrete is very brittle material, once a crack forms, the crack quickly grows and we're able to separate the material. So if you look at the stress that it takes to separate a piece of concrete, that is shown by this light blue line here. FT is where the crack forms, and once the crack forms and as the crack starts widening, the stress that it takes to pull the material apart decreases very rapidly. The minute I start putting some fibers in there, the fibers will arrest the crack, and at low dosage of fibers, I get some stress recovery. Basically, the cracks are able to, or the fibers are able to hold the crack and actually give you some resistance as the crack is being opened. And if I increase the fiber dosage, I can even get to the point where the resistance coming from the fibers exceeds the strength of the material. And when that happens, I get multiple cracking. So instead of having one big crack, I get 50 smaller cracks that are formed in the material. So there are different types of fibers that are currently in use, and they range from synthetic to glass, asbestos, carbon, and even natural fibers. And of course, steel is the most prevalently used fiber. And the usage would depend upon the cost to benefit ratio, the ease of application, and whatever improvement that I'm looking for in performance. Now, some of the uses of fibers that are currently being used or where we are putting them to use is in shotcrete applications. Now, whenever we have tunnels, as the excavation or blasting takes place, the rock mass has to be stabilized. And the way it's traditionally done is using conventional reinforcement and then gunniting. So one creates a layer of concrete, which is gunnited using conventional reinforcement. Now, the newer applications is to shotcrete it, where basically concrete is directly shot onto the blasted surface or excavated surface, and it contains fibers in it. So there's no need to put a reinforcing mesh. And using this shotcreting technology with fibers now, several tunnels have already been made in India, including that all-weather route in Leh, Lahul, Spiti Valley tunnels in Himachal Pradesh, Jammu, have been made with this shotcreting technology, where steel fibers have been used instead of conventional steel reinforcement. Now, the other use of fiber reinforced concrete is in these jointless pavements, and these are done for container terminal yards, where extremely heavy loads are piled on to onto very small areas of concrete. And these are large spans of concrete slabs without joints. And the only way we can keep the slab from cracking and from those cracks from opening and becoming wide is by incorporating fibers. And now design procedures for the use of these fibers in these pavements are also being standardized so that they can be used. And a live example of this is the container terminal yard of Amazon, where basically, which has been designed for the super heavy loads. And it's essentially one big jointless pavement made with steel fibers in concrete. Metro tunnel lining, where the precast elements are now being lined with fibers instead of conventional reinforcement. The other area where fibers are finding big use is small synthetic fibers are being used to cut down on cracking in concrete. Oftentimes, concrete cracks because of shrinkage, where when concrete starts drying, it cracks. And even sometimes curing doesn't help when these cracks develop. So basically, the use of micropolypropylene fibers, these are very, very fine fibers made of polypropylene, which are added to concrete at a very small dosage of about 0.2% of the volume of concrete. And they're able to mitigate these cracks that form in concrete. And glass fibers have been used and are used extensively for architectural concrete because they're able to cut down on the appearance of the surface cracks that come when concrete dries. And one big example of this has been in the terminal building in Mumbai International Airport, where the white, the surface, or the entire white concrete contains the glass fibers, which keeps it from developing these pattern cracks, and one gets look and feel of stone, which is a flawless stone, or look and feel of the flawless stone is reproduced in this concrete. Architectural concrete is extensively done with glass fiber reinforcement in here. Just an example of architectural restoration where these figures and figurines were essentially made in stone. They were replaced by glass fiber reinforced concrete cast elements, where the glass fiber basically holds the material together and doesn't allow it to crack. One more application of fiber reinforced concrete is in ballastless track technology for high-speed trains. The conventional design, which is patented, it basically calls for very heavy steel reinforcement. Now, with the use of fibers, basically there's a project where we were able to bring down the utilization of steel. So now we're able to use steel much more efficiently, and by using macro synthetic fibers at about 5 kilograms per cubic meter of concrete, we are able to reduce the steel consumption from 1347 square millimeters per meter of the pavement to 785. Basically, drop it down to almost half of what was initially added. At the same time, without compromising the crack opening, we were able to do this by achieving a crack opening of 0.2 mm, which is within the norms of serviceability requirement specified in the Indian code. So these are essentially the applications of fibers, which up to this point have essentially been non-structural. But now fibers are also coming mainstream in structural applications, where if I add fiber to concrete and we look at improvement in the shear performance of concrete. So we've tested concrete beams without shear reinforcement. So without shear reinforcement, if I test a concrete beam, it basically fails in shear. So VF equal to 0 is where I have no fibers in the concrete. But the minute I start adding fibers to the concrete, you see that I start improving the load resistance. The peak load starts increasing, and also the ductility starts increasing. So at about 0.75% volume fraction of the fibers, so 0.75% of the total volume of concrete is in the form of these steel fibers. One, we are able to achieve a tremendous improvement in the shear capacity and also essentially produce a nearly ductile response where basically the load remains constant for a very large amount of deformation. So this is mainstreaming of application of fibers in structural applications. So this is as far as conventionally mixing fibers as alternate forms of reinforcement in concrete, which would allow us to reduce the requirement of conventional reinforcement bars in concrete. Now, as we're progressing, alternate forms of concrete are also finding their way into mainstream applications. One of the main applications deals with ultra high performance fiber reinforced concrete. Now, this is a form of concrete which is engineered. So basically, we start looking at the material from the nanoscale. We engineer the material at the nanoscale. And then at the micro scale, the meso scale, and we get tremendous improvement in performance in the macro scale. And this is done by packing of the material. We basically pack the material by carefully paying attention to the different scales, packing at the nano, at the micro, and the meso scale. We basically introduce a very high fiber volume into the material, and the high fiber volume is introduced through processing. And I'll talk about processing in the next few slides. And by doing so, we are able to produce this UHPC, ultra high performance concrete, which basically gives us very high tensile strengths of about 30 megapascal, and basically gives us a very ductile response. Basically, it cracks, but it does not fail. And this UHPC can only be achieved by processing, which requires basically packing a lot of fibers into a volume of concrete. And I'm just showing you a CT scan of what one of these UHPC materials looks like, with a very high fiber volume packed into a very small volume of the material. And one is able to achieve this level of ductility. This is a beam, a small beam, a very thin beam made of UHPC, which starts deforming like a steel beam. So what do I gain from this? Of course, this is a more expensive material because I have to pay a lot of attention to processing the material. But the gains I have now is I can start using this material just like steel. Now, this is a comparison of what I can achieve with this UHPC. So just to show you, this red here is a steel beam. The performance of this steel beam can be matched by conventional reinforced concrete of a much larger size. So that is shown here. So a reinforced concrete beam of a much larger size would match the performance of the steel beam. If I go to pre-stressing, I can basically reduce the beam size, and I can also make the beam more efficient in its use by using an ice section. Then I can basically reduce the size a little bit. But when I go to UHPC, which is shown as ductile here in this photo here, you can see that we can start matching the size of the beam in terms of performance with this ultra high performance concrete. So basically now through processing, we are able to now start producing material which gives us the same level of efficiency as structural steel. But of course, now we have to start looking at it in terms of manufacturing. So we'll have to manufacture this material. And just to give you show you an example of a real beam that was tested, it is about 13.4 meters in length. It's a pre-stressed beam, and we were able to achieve behavior that essentially resembled steel beam in its behavior. This ultra high performance concrete is now being pushed into mainstream. This is the advantage we gain is because now this material is very strong in tension. It is very ductile. We're able to get much better forms. We of course don't need any steel reinforcement in there because now this material is packed with fibers. And basically we are able to achieve much slender structures. Here's a photograph of an arch bridge, which is made with this ultra high performance concrete, and it has no steel reinforcement in it. And one is able to achieve 1:30 slenderness ratio, which is not possible in conventional concrete, where we start approaching what we can get with steel using this material. So this material is also slowly now finding its way into or being mainstreamed. Advantages we gain is much lesser use of the material because this material is so efficient. We are able to basically use it in much lesser quantity and give structures which basically perform on par or better than conventional structures. So just to summarize on the alternate internal reinforcement, we basically now the alternate internal reinforcement is finding its way. It's being mainstreamed. One of the biggest challenges we have is lack of design codes, because this is new. The design codes have not kept pace. Also, our conventional design procedures are strength-based. We basically have been taught about strength. We only think in terms of strength. But when we start using alternate reinforcement, we have to start looking at ductility. And that basically means that our codes have to be revised. Basically, they have to be updated. And that is work that is basically currently ongoing. Finally, basically, I want to touch upon rapid methods of construction. There are alternate forms of construction that are coming mainstream, alternate forms with integrated reinforcement. So basically, reinforcement which is integrated or knitted together in the form of 3D reinforcement. And this is being adopted in textile reinforced concrete, TRC. and also in the form of metal reinforced concrete structures, where we have this 3D integrated reinforcement, which is factory fabricated. And then it is cast in the on-site in the form of 2 layers of concrete, 2 widths of concrete, which are separated by an EPS core. The EPS core serves the purpose of providing sound and thermal insulation. So overall, the construction is very fast. We can rapidly integrate these EPS panels with integrated reinforcement, and simply shotcrete or cast concrete structures, which are much faster and thermal efficient. So these are alternate forms of construction that are also coming mainstream. Now, finally, I just want to touch upon this before closing, and that is, as we are going along, we are requiring our buildings to be taller. They have to be built faster, and of course, in doing so, we have to push the envelope in terms of overcoming the obstacles imposed by nature. We are basically pushing the envelope in terms of what we expect the material to deliver, what we expect the structure to perform against the elements. If you look at the skyline here, starting from 1930s, where Empire State Building was the tallest structure, going up to the current tallest building, as you see, this has steadily gone up. We are going higher and higher. And Burj Khalifa today, which is the tallest building today, is about 850 meters tall. So basically, we're almost 1 kilometer in height. Now, the other important thing to note here is 1930s and right up to somewhere around here, up to I would say around 2000, the main structural system that was used in all these tall buildings was steel. But going to the left of Type A 101 now, concrete is becoming more and more prominent in structural systems. The main structural system in Burj Khalifa is a concrete system. So concrete now is coming mainstream even in super tall buildings. And that is happening because of developments in technology. Now we are able to deliver concrete at 800 meters of height. So technology which allows us to take concrete 850 meters in height is now available. And that, I think, has revolutionized construction of these super tall buildings. Now, just to give you a snapshot, if you look at the super tall buildings, of the 100 tallest buildings in the world, 59 of them are in Asia and 23 are in Middle East, which only leaves 18 in the rest of the world. So for once now, at least in high buildings or tall buildings, Asia is leading. We have more tall buildings either under construction or which have been completed, which are in Asia compared to the rest of the world. And concrete is now the dominant material as it's used in construction of these buildings. And just to consider the 2 tallest buildings, whether it is Burj Khalifa or the new building that is conceived in Jeddah, the Jeddah Tower, which is going to be 1 kilometer tall, basically the structural systems of these 2 super tall buildings is made of concrete. Just a snapshot of the buildings as we go across. 1930s, the light blue indicates steel. 98% of the super tall buildings were steel. And as we come across the decades, and you see that in current situation today, concrete or concrete steel composite is the predominant form of construction used in the super tall buildings. And this has happened because concrete, of course, has advantages in terms of strength and durability and affordability. It is much, much cheaper than steel or other construction materials. But primarily, the construction technology has allowed us to overcome this obstacle where now we can deliver concrete at 850 meters height or higher than that. Now, so coming to this last part of my presentation where I want to talk about transporting and placing. This is where I think in the last 2 decades, tremendous amount of development has taken place in the technology in terms of pumping, self-leveling, self-consolidating, and formless placement. So these are things where construction technology, particularly with concrete, has made tremendous advancements in the last 2 or 3 decades. So we're talking about now pumping and self-leveling concrete. This is concrete that can be pumped to a great height. It levels by itself without any vibration. And the next paradigm is, of course, looking at digital manufacturing, where we're talking about concrete which keeps its shape once it's pumped, and I'm able to make shapes out of it. So a little bit about self-consolidating concrete. Our conventional, the way we were taught concrete was in the form of of increasing flow or slump of concrete. So we only thought in terms of slump. The flow of concrete was never given much importance. So the way we were taught concrete is to basically make concrete more fluid by adding water. The problem is if I add water, concrete tends to segregate. And when I have heavy congestion of steel, just having a high slump concrete will not do it, as I'm illustrating here. If I simply add water, I will still have either segregation or I'll have these honeycombs where concrete does not penetrate between the steel. And more examples of a cast in situ pile where concrete just did not penetrate through the reinforcement cage. And
I think there is a bandwidth issue, is it?
So he has suddenly gone offline, sir.
Oh, is it? I think a bandwidth issue should be the same.
Yeah, could be power or something.
We'll wait for a couple of minutes,
Sure,
1 or 2 minutes. We will wait so that I think. But it is connected, I believe, no?
It's connected, but there's no voice coming from his end, sir.
Okay.
Dr. Subramaniam, sir, can you hear us? We'll wait for him, sir.
Yeah, we'll wait.
Sure.
I think it is self-compacting concrete now.
Yes, yes.
So there has been some connectivity issue. So I would request the viewers to just let us give 1 or 2 minutes for the speaker to come back. So it was a wonderful presentation on sustainability in concrete and the usage of alternate materials that can be used. So I think already the time, we have overshot the time. So some of the questions, of course, when the speaker comes back, we can take. Few question was on whether we are manufacturing rapid hardening Portland cement. Yes, as I was showing you in my presentation at the beginning, yes, we are manufacturing rapid hardening Portland cement, especially Ramco Superfast, which is being used for many of the precast works. So that is what is being used. So we are doing that. So it is in fact a rapid hardening Portland cement, and there were questions on whether how much percentage of fly ash can be used at site. Although there is limit on usage of fly ash in PPC, as was mentioned by the speaker, between 15 to 35%, and Portland slag cement uses between 25 to 70%. But when we use fly ash at site, I think we need to do the concrete trials and then see what is the optimum percentage of fly ash that can be used. But then, again, we need to look at the properties of fly ash in terms of what is mentioned in the IS code in terms of lime reactivity, in terms of the fineness of the fly ash that is being used. So I think once we are sure about the properties of fly ash, then it can be used at site. But then we need to be cautious about that. So I think that answers the first two questions. In the lab, we are able to get the 28-day required strength for M50 for 70% fly ash. Can we use the same in the field? Is something that we need to look at by looking at the properties of fly ash and the mixed design that we are using at site. So based on that, I believe we can use the proportion. And what is the state of art of geopolymer concrete? Yes, tomorrow at 11 a.m. we have again a webinar on geopolymer concrete by Dr. Bikshma. I think he would be able to clarify on geopolymer concrete in detail, wherein fly ash is being used along with an alkali activator. So more on that in tomorrow's webinar at 11 a.m. So before we sign, Engineer Anjana Unnikrishnan for giving the vote of thanks. Over to you, Engineer Anjana. You are there. Dr. Rameshwar Rao.
yeah, can you hear me?
Yes. Engineer Anjana is there?
Engineer Anjaya, Honorary Secretary.
Yeah, Engineer Anjana, Secretary of Institution of Engineers, Telangana chapter. He would be giving the vote of thanks. Over to you, Engineer Anjana. I think there is some problem with the bandwidth.
Yeah, can I request Dr. Rameshwar Rao, sir, to take over because we couldn't get sir earlier also, Anjanaya, sir. Can I request Dr. G. Parameshwar Rao?
Yeah.
Sir, now Subramaniam sir
So you can.
may join now, sir, within 2 minutes.
No, I've just joined actually. Can you hear me?
Okay, fine. Yeah, please continue, sir. I think you can give up the concluding remarks, please.
I will share the
Yes, over to you, Dr. Subramaniam. Over to you.
Okay, just 1 second. I just have a few slides. I just want to conclude with that.
Fine,
So,
fine. Sure. We will.
You can load your PPT now, sir.
yeah, just 1 second. For some reason, I don't know if it's, am I able to share it or no?
No, it is not coming. We are not able
Coming
to.
through.
We are not able to see it. Yeah.
Okay, sir. 1 second. I will move it back to me and then. Hang on, sir. Can you try it now, sir?
Just 1 second, yeah. For some reason, it's not allowing me to share the PPT. That's
All right.
that's okay. So I think I'll pretty much I'll conclude here. I mean, I think I had a few more slides which basically talked about
All right.
the use of the concrete technology, where we've gone to the point where we can control the flow behavior, deliver concrete of the required flow properties, so that now we are able to pump the requirement to a 1 kilometer length or higher, and that's allowed us to use it in high tall buildings. Finally, by understanding the flow behavior, we are able to manipulate the flow behavior and get into additive manufacturing, where not only are we able to pump great distances, but the concrete basically now takes the shape as it leaves the barrel. And we are now able to shape concrete in different forms, and that is taking us into the domain of 3D printing. And 3D printing is now becoming mainstream, and I think it's just a matter of time, maybe in the next couple of years, or the next few years, we'll have 3D printed concrete structures becoming reality. So with that, I'd like to conclude. I apologize, the last few slides didn't load up, but I'd be more than happy to take any questions on these topics. And the whole point that I was trying to raise is sustainability from concrete, sustainability in concrete when it comes to construction has to be addressed from different fronts. One is material usage, more efficient use of the material, less use of the carbon intensive cements, therefore looking at alternate binders, more efficient forms of construction which allow us to do more with less. That is, we're able to construct structures which last longer with less use of materials, therefore they deliver performance. And then finally, being able to deliver structures which are able to overcome the problems faced by conventional construction and get into more rapid forms of construction, where we're able to deploy structures much more rapidly in a more efficient manner. So with that, I'd like to conclude and open the floor for questions. And thank you for your attention.
Thank you. That was a very wonderful presentation. In fact, you had covered all the aspects of how to make concrete sustainable. There is an interesting question by Mr. Kondal Rao. He says, excellent presentation, but there is a lot of mismatch between research outcome and actual field application. How to bridge this huge gap?
One of the things is with most technology, any technology, there's always a gap between what is done in research and when it sees field use. That is always true in any field of engineering. So in some fields of engineering, perhaps that gap is much shorter. I mean, if you look at something like telecommunications, perhaps that gap is maybe years. In construction and construction technology, that gap tends to be a little longer. But I think slowly we're starting to bridge it to the point where several of these things are now coming mainstream. And biggest challenges we often face with the use of with construction technology and mainstreaming alternate technology is with lack of standards. Everything we deal with, we need standards and we need codes, because everything we do is ruled by a set of design codes or codes of practice, and those take time to develop. So because of that, mainstreaming often falls flat. So it doesn't work. So, or it doesn't, commercially, it doesn't take off. So that is the lag. And now slowly we're also starting to work on that aspect, where as researchers, as academicians, we're trying to bring out these codes also in a much faster manner, so that we're able to mainstream some of this technology much faster.
Dr. Rajendra Prabhu has a question. What is the performance of alkali-activated cement concrete at elevated temperatures?
It's in fact much better than regular concrete. I didn't touch upon that aspect, but basically it behaves like a ceramic, and it has excellent high temperature properties. So one of the alternate uses that it's being explored at is for high temperature applications, where we're looking at developing high temperature coatings, high temperature sacrificial layers made of this geopolymers, which can be used to enhance the fire rating of structures.
What is the flexural strength and elastic modulus of alkali-activated cement concrete with respect to Portland cement concrete of same strength?
Compressive strength is one can achieve much higher than regular cement concrete.
Okay.
Strength again, materials. It's going to be much smaller. Yeah. Right.
So other question was all right. There was this interesting question in the lab. We are able to get the 28-day required strength for M50 for 70% fly ash. Can we use the same in the field? So, question by Mr. Anumanta Rao.
Been used.
So I think that's it. So we have been able to cover most of the questions, and thank you so much, Dr. Subramaniam.
This push.
Okay, there is some
structures have been made in Australia and China. Alkali-activated materials, and it's not simple structures. Also done high-rise multi-storage.
Okay. So thank you so much for that interesting presentation, and let me go to Dr. Rameshwar Rao for the vote of thanks. Over to you, sir.
Okay. Thank you very much, sir. Really, on behalf of Institution of Engineers Telangana State Center, thanks to our Subramaniam Garu. Really excellent presentation, and also thanks to our President Engineer Narendra Singh ji, and also thanks to Engineer Anil Kumar Pillai, General Manager, Ramco Cement, Chennai. Really, this is the centenary year. We want to do many programs, but because of COVID-19, we are unable to do in our Institution of Engineers. We are doing all programs and only webinars. We are going to be doing many programs in coming days before September 15th. 15th September is the last, the centenary year closing day, last day. We want to do many programs. I wish all to be come together and also become a member of part of the celebrations. Thank you one and all.
So thank you so much, Dr. Subramaniam and Dr. Rameshwar Rao Garu for coming as panelists. And then I think we will wind it up. The time is up. It's already 12:45, and it was a very interesting discussion on sustainability. And let's meet tomorrow at 11 a.m. For another presentation on geopolymer concrete. So with those few words, let me sign off from today's webinar. Thank you so much.
Thank you.
Thank you.
Thank you.